Michael Barker. Michael is a software engineer with more than 2 decades of experience across a wide range of industries. He has spent the last 13 years working on financial exchanges, brokers, and high-frequency trading systems. He was the lead maintainer of the LMAX disruptor for several years, and he currently subcontracts to Adaptive Financial Systems as a core developer on the Aeron project. So just before we get started, we got a poll that we're gonna be launching now. I'll just launch it. And then just please make sure you submit your answer just before we get started with the presentation.
All right, shall we make a start? And I will come back to the poll a little bit later on during the talk, and we'll have a look at some of the results of that.
Yeah, yep. Just say, so if you, I think you can see the poll if you click on the top right. There's a poll. So, and then you can always click on that. So yep. Go for it, Michael.
Excellent. Well, thank you very much. My name is Michael Barker, and I am going to do a talk today about the gory details of Aeron Transport and Archive. I'd like to say many thanks to the FinTech Devs Meetup group for inviting me to speak again. I gave a talk last year around Aeron, but that was a talk was more about distributed systems and architecture and that side of things. This talk is going to be a little bit more nuts and bolts. We're going to dive into some core details of how Aeron works. And a big portion of this talk is going to be based around software performance. So I'm going to start off. What is Aeron? Aeron is a library to create high throughput, low latency, and fault tolerant distributed applications. So what does that mean? Well, Aeron's pedigree is based in an area of financial technology that we often refer to as capital markets, and that largely encompasses things like high frequency trading, financial exchange design, brokers, and that sort of thing. To give you an idea of the sorts of companies that are currently using Aeron, here's a sort of a snippet of some of our paying customers. If you look here, you may or may not recognize some of these. You've got people like the CME Group, which is the Chicago Mercantile Exchange, a big exchange out of the US. gRPC is a very highly respected high frequency trading platform. So a lot of the demands that are on Aeron really focus on its performance. And these are some of the most performance demanding applications you can get. They're sort of up there with things like games or real-time military applications, all that sort of thing. So, quick agenda, what I'm going to go through today. I'm going to start off with a bit of a component overview. I'm going to look at the Aeron stack and how the various pieces fit together and what is Aeron made up of. I'm then going to dig into the architecture. Specifically, I'm going to look into the architecture of Aeron Transport, and you'll find out what that is in a little while. Do a little bit of a primer on the API and how a user might actually access the API and how that sort of impacts some of the design. And then we're going to start to dig into performance. So I'll provide some examples of the actual performance of Aeron compared to a reasonable competitor, some of the design principles that we used, and then some practical examples, look at the implementation, some of the data structures and algorithms, a little bit of code before summing up. So first off, the Aeron is a stack, and it's made up of 3 main components. And at the very bottom of the stack, sort of making up the core, is what we call Aeron Transport. And Aeron Transport is a layer 4 protocol, and it sits in the same part of the OSI stack as you would expect something like UDP or TCP. It happens to be implemented on top of UDP, the same way you could actually implement TCP on top of UDP as well, but it sits at the same level. But what we've done is we've taken what we believe to be the best features of these two transports. First off, from UDP, it is both unicast and multicast. This means you can set up a situation where you're going from a sort of point to point between two machines, or you can utilize multicast to send a message from one machine and allow your underlying network infrastructure to replicate that message across multiple machines in a scalable manner. The other quite cool feature is that it's message oriented. That means that you either get the whole message or none of the message. This contrasts with TCP, which is byte oriented. TCP doesn't have its own message framing layer. That's something you have to do externally. You can get lots of fragments of messages, so you layer something like HTTP on top of it to handle that. But we pull some pretty cool features from TCP as well. It's connection oriented. So there's a setup of a relationship between a sender and a receiver. It's reliable, but it's reliable in the same sense that TCP is reliable, in that once you have a connection established, that any messages that are lost can be nacked and redelivered. It is ordered, so the order of messages that you put into Aeron is the same order that come out. It also supports flow control. This is a mechanism by where you prevent a very fast sender from overrunning a slow receiver. This is quite configurable, and it's also optional inside of Aeron. This is really important when we look at things like multicast. The reason for that is it's impossible for us to know ahead of time how you actually want to slow a sender down in a multicast scenario. Do you want to go as slow as the fastest node or the slowest node or somewhere in between? And the final feature we take from TCP is congestion control. And this is where you're trying to prevent a fast sender from overrunning a congested network. This is really important in environments where you're using congested or heterogeneous networks like the internet. Our customers make heavy use of that in environments where they're doing things like ingress from an on-premise system up to the cloud, or WAN connections between data centers, or cross-region on the cloud as well. Being able to apply congestion control in these environments is very helpful. The next part of Aeron I want to talk about is Aeron Archive. And this is where we're taking a step from having just sort of reliable messaging to durable messaging. This is where we're able to take the streams of messages that you've set up in transport, record, replay, and even replicate them between nodes. This is quite different to what most people might expect with a durable messaging solution. It's quite different to a system like Kafka. We don't create a central broker in Aeron because of the additional latency that would be incurred. The way that Archive works is that you're effectively watching messages go past as they're being sent from one machine to another, or potentially received on one endpoint, and on the same machine, you're storing that data to disk. So we avoid the sort of centralized store, having a centralized broker holding logs of information. And I'm going to talk a bit more about how that fits together as we go on. And the final component that I want to mention is Aeron Cluster. This is the one I talked about last year quite a bit. Cluster is a container for building fault-tolerant services. You're able to implement your applications as replicated state machines and make use of a raft-style infrastructure to give you the various reliability guarantees. I'm not going to talk much about today, but if you're interested in this sort of stuff, have a dig around replicated state machines. They're a really fascinating topic. So let's have a little bit of a look at the architecture that underlies Aeron Transport. It has quite a unique design. So as I mentioned earlier, Aeron Transport is very much a peer-to-peer style system. So we don't have a centralized broker. The main reason for this is that halves the amount of network transits from your source machine to your destination machine. But on each machine, we have two pieces. We have what we call the client and the driver. And they communicate with each other via IPC. So this means your media driver and your client can sit in separate processes. So if we have a quick look at the media driver first, there's three main components that make this up. There's the sender, the conductor, and the receiver. And the sender's responsibility is to take messages provided by the user application and send them out on the network. And then similarly, you've got the receiver, which is there to take messages off the network and pass them back to the user application. And in the middle, we have this thing we call a conductor. And these three components generally each run in a separate thread. So we generally have 3 threads running in the system in most production deployments. And the conductor's responsibility is to take some of those slow path operations away from the sender and receiver. These are things like name resolution, the construction of sockets, binding sockets to particular ports. Those types of slow operations can be done in the conductor. And then we can share that information with the sender and the receiver. There's a little internal messaging bus between them. But what gets really interesting is the way that we communicate from the client to that driver. You'll notice those little sideway laddering type things that exist between the publisher and the sender. And these are what are known as the term buffers or the log buffers. And this is kind of a fundamental data structure that makes up Aeron. I'm going to talk a lot in detail about how those work. But the way that you would send some information between clients is you've got the publisher, which is the user application. And then this term buffer is wrapped up by an object we call publication. The publication offers messages to, the publisher offers messages to the publication, which are then picked up by the sender via these term buffers and pushed out to the network. And then similarly, when we receive messages via the receiver, they are then pushed into a term buffer, which is wrapped by an object we call a subscription, and the user application can pull that information from there. And then we have these two conductors that talk to each other. And this is where the user application will do things like adding a publisher or removing a subscription or doing all of the operations used to set up the communications. That's what we generally refer to as admin events. But this idea that we can have this shared memory transport between the media driver and the client gives us some really neat benefits. It means that we can have the media driver run either in process with the application or out of process as sort of like a separate daemon. This creates a couple of useful benefits. First off, when we first wrote Aeron, we wrote it in Java. And one of the tricky things with Java is you're often having to deal with garbage collection. We spent a fair amount of engineering time making sure the Java implementation of the media driver doesn't do any allocation on these fast paths inside the sender and receiver. The idea being that you wouldn't create situations where the media driver would end up having to do a garbage collection store. But we're application might not have the same level of discipline, and it may garbage collect and it may store. So having the media driver run in a separate process means that the user application can garbage collect and it can store, but the media driver will keep running and it will keep taking data off the network and pushing it onto the network, resulting in a more predictable system and allow it not to face situations of things like packet loss that can often be caused by a stored system. The second cool benefit that we get out of it is that we can actually write the media driver in a separate language. And in fact, we've written an implementation of the media driver in C. The main reason for that is that it allows us to access some interesting lower level systems like DPDK or EFEI. And the final really interesting thing that came out of this was actually something that came from one of our customers. They were playing around with containerized deployments, specifically Docker and Kubernetes. And they were running into the performance issues that you often run into with these, with using the virtualized networking stacks. Most people who want to do reasonable performance systems using Docker are doing things like host-based networking. But the interesting thing that this company did, and they talked to us about, was they took the media driver and they installed just the media driver on the host OS. And they were able to deploy just the clients inside of the Docker containers or the Kubernetes pods. This meant that the communication between the clients and the containers and the driver and the host OS was simply just by shared memory. They were just able to map the file systems through. This remained as efficient as if they happened to be on the same container or on the same OS. but it allowed them to make the really best use of the underlying host OS's networking capabilities. So it gives some really interesting deployment options, being able to make these cool sorts of tunings. So that's a sort of a brief idea of the architecture. It's useful to have a little bit of a look at the API. So this is sort of a very basic cut-down client. Now, I mentioned previously that the client and the driver use a sort of shared memory transport. And this is often represented using an in-memory file system. The typical one we use in production deployments is defshm, which comes under Linux. And it's that file system path that creates the linkage between the Aeron client and the driver. So if you scan down, you'll notice that there's a mediadriver.launch call. And you'll see we're configuring the context there with the Aeron directory. Then we have the associated Aeron.connect. This creates the client and connects it to the driver. And you'll see there in its configuration, it's using the same path. So that's how we connect the client to the driver. The second part that we have is what we call the channel and stream. This is how we set up the actual movement of messages between endpoints. You'll notice that we've got this endpoint described here. It happens to be localhost on port 2001. And we will create a publication and a subscription using that channel information. Publications and subscriptions are unidirectional. So if you want to create a bidirectional communication, you need to set up a pair of them to send messages forwards and backwards. The other interesting parameter here is the stream ID. Stream IDs allow us to multiplex multiple streams down the same IP address and port endpoint. This means that you can create multiple virtualized streams without having to use large numbers of ports. Then how do we actually get the messages onto the bus? Well, we have a method on publication called offer. The idea we pass in the message along with the offset into the buffer and its length. This is a non-blocking call. So if this fails due to the publication not being connected, or there's some sort of back pressure from the downstream subscription, this will actually return an error code saying the data couldn't be delivered. It does not block and wait for the message to be delivered. So it does push the error handling back up to the user. Similarly, on poll, we call this method and we get an associated callback. And again, the subscription.poll method does not block either. If there's no message data to be received, it will return immediately. Or if there is data, it will come back, apply the callback, and tell you the number of fragments that have been processed. The other part of the API that I wanted to look in, or this part of the API that I wanted to delve into in a little bit more detail, is the structure of that channel, that URI. Because we can make subtle changes to that URI to change the behavior of the system we're using. But the idea of encapsulating it in the channel URI is so that we have API compatibility. We don't change the way that we interact with the publications and subscriptions, we just change. So this is the idea that we're creating a publication and subscription. The subscription is listening on that endpoint, 10.0.0.1, 10,001, and the publication, or even potentially multiple publications, will be sending them. If we're wanting to do multicast, the subtle change here is we're using a different IP address. This sort of IP address will be familiar to people who have used multicast before, but multicast has a special reserved range amongst IP addresses that by convention can't be assigned to machines. They can't be assigned to special machines. They work as groups that are implemented on the network switches. So when you join into a group by creating subscription, then you send to that particular address using a publication, the network switch will take care of replicating it to any particular node that has expressed interest. But there are a couple of others as well. The next one, the IPC channel. So one of the interesting things that we talked about during the development of Aeron was saying, well, could there be an optimization when we have two processes or two threads on the same box that actually want to talk to each other, perhaps via localhost? If we have that, well, there's a turn buffer for the publication and a turn buffer for the subscription. Shouldn't we be able to merge those two things together so we just have the publication and subscription sharing those turn buffers? We initially thought about trying to do this so transparently. So if we detected that it was a local host connection, we could try and cut out the middleman. Turns out this got very complex. It was not possible to do reliably, and it is actually not what really people wanted. So we have a special channel, and if you specify the IPC channel, what will happen is the media driver will set up a single shared term buffer between the publication and subscription. And once it's set up, it actually gets out the way. So the sender and receiver are not involved at all. You just have your publication and subscription asynchronously passing messages between them using the same shared in-memory buffer. And this ends up being very fast. And this is really useful for processes on the same machine, or even just threads on the same machine as well. And finally, we have a thing called spies. And I alluded to spies earlier when I mentioned archive. When we want to archive something or write it down to disk, we don't want to have to create an additional network connection, and we were wanting to have it happen potentially on the same machine. So if you imagine we wanted to record the traffic going to the endpoint 10.0.0.1, we add this additional spy prefix. That creates us a subscription that's sharing the same term buffer that the publication is using, but is receiving that data very quickly. And this is in fact what archive uses to record data as it's been sent out onto the network. So I thought I'd take a little bit of a pause there. We're going to jump into some interesting stuff around performance next, but let's have a little quick look at the polls. So we got a total of 7 responses. We got 4 saying, so the basic idea of the poll is what aspect of performance is most important in your organization. So the majority of people, about 4 out of 7, were saying transactions per second, so basic throughput. Two people have indicated that latency, certainly where I work, latency tends to be the most important thing. And the other one was UI responsiveness. Interestingly, nobody's probably working on heavily games on mobile devices where power consumption can be the dominant feature. So again, that's quite interesting getting that aspect, and it's not unexpected. Certainly my experience in the industry and various industries is a core focus on latency tends not to be the main focus. Most people are trying to look at the overall throughput. That tends to be very heavily relying on things like data analytics. But I think sometimes latency is a little bit underestimated in terms of performance, because it can actually have a big impact on a number of things. And also UI responsiveness is interesting because it's often you're hiding the overall latency or throughput issues in your system by ensuring you can get information back to the user quickly and allowing things to happen a bit cleaner, a bit more cleaner and more asynchronously in the background. So that's kind of an interesting response there. So now I'd like to dig in to some interesting stuff on performance. So I've mentioned that Aeron is designed for these capital market systems, these high performance systems, but I haven't really quantified that. I didn't really give any information on just how fast it is. So we've done benchmarks, we've done quite a few benchmarks, and I'm going to share one of them with you. This is a ping pong latency style benchmark. This is pretty common style of benchmarks when you're working on systems that do care a lot about latency. Quite often it's what a lot of our customers tend to care about. So what we've done here is we set up a bidirectional stream. So this is using gRPC's bidirectional streaming. And in the case of Aeron, we've set up a situation where sending messages out and sending them back. And we're sending them at a fixed throughput rate. And what we're measuring is the latency of every single message going out and coming back again. So we put a timestamp on the message as it goes out. When it comes back, we calculate the delta, it gives the latency. And we create a histogram of all of the messages. Because what we tend to be interested in is we're looking at this long tail. Because in financial trading systems, it's not only having low latency, but it's also having predictable latency is really important. The reason for this is that latency represents risk. If you're running a financial exchange and you're providing a service to a series of market makers who are effectively vendors, and if they are seeing high or potentially unpredictable latency, that's going to create risk for them because potentially they've got orders in the market and if they can't very quickly go in and cancel those orders, if the market moves in a direction that's unfavorable, they're going to get quite nervous. So what they will often do to mitigate that risk is either not use you as a platform, or they will widen their prices. They'll create a larger spread between the bid and the ask. This is effectively a way of them making their prices more expensive. And this ends up making your exchange poor for users because your prices are more expensive, or it's going to cut into your margins. So there's a very strong correlation here between business value and latency. But let's actually have a look at some of these numbers. So something we might be able to read, I apologize if you can't, but let's first look at the Aeron C driver, the Aeron Java driver, and gRPC. Now, if we look at the typical case, in this case, I'm going to use the median values. We've got the Aeron C driver and the Aeron Java driver around about the 18 or 19 microsecond range for a message to go out and come back. And this is on a reasonably well optimized 10 gigabit network, on-premise network. If you look at gRPC, gRPC is nearly 4 times that. So the latency on the typical case is much higher. It's around about the 85 microsecond mark. But where it gets really interesting is when we start looking at the 4 nines percentile. Here we're looking at roughly 1 in every 10,000 messages. And we can see that this spikes up significantly for gRPC. So with Aeron, with the Aeron C driver and the Aeron Java driver, around about the order of about 100 microseconds. But with gRPC, we're up into around about 13, 14 milliseconds. This is 2 orders of magnitude higher. The other thing I want to look at now is if we have a look at some of these other fields, you'll notice there's an Aeron C-onload and an Aeron Java-onload. Of a certain brand of network card provided by a company called Xilinx. It tends to be very popular in the financial trading services space. And what they do with onload is onload provides a library that looks almost exactly the same as the Linux networking libraries. It has methods like send, receive, open, socket, bind, epoll, send message, sending message, all those libraries that you normally use in C. But what it does is instead of sending the data the normal path through the operating system kernel, it bypasses it and goes directly to the network interface cards. And this can add a really decent boost because a lot of the overhead in sending a packet across a network is actually caught up inside the operating system kernel with things like the system call overhead and a lot of the interpretation it needs to do internally. But let's have a look at the numbers. The difference between the Aeron C and the Aeron C onload, similarly for Java, is we go from this 18 to 19 microseconds down to around about 7 or 8 microseconds. So we've got around about a halving of our latency. So proportionally, that's pretty good. If we look at gRPC, we can look at the latency differences going from about 85 microseconds down to about 75. Now we've got the same absolute performance improvement. We're sort of, it's at around that 10 microsecond mark, but proportionately, it's not that much. It's only about 15% improvement. So you're not seeing as big a win from using a tool like this, certainly proportionally. So this is one of the design ideas behind Aeron. The idea is what we're trying to do is provide a software system that has as little overhead as possible. What we're trying to do is create it such that if you provide big improvements in your network, Aeron is able to pass those improvements onto your application. It correlates with a statement that one of my colleagues, a guy called Todd Montgomery, said. He said, if your networking or if your messaging system is not able to saturate your network, then you've got more work to do. So there's another interesting point that's actually kind of left off this chart, is that we've been running these tests. We put Aeron up to 100,000 messages per second for this particular test. The thing with gRPC is we couldn't actually reach those throughput rates. So with all of these numbers, even with the gRPC lagging behind Aeron, it's actually only running at 25,000 messages per second. So that sort of gives you a general idea of the level of performance we've managed to achieve with Aeron. So the big question is, how do we do it? How do we build a platform that's trying to achieve these quite challenging performance goals? The one thing I have learned about building software like this is that you can't build it naively. You can't just build something that basically works and optimize it to be fast. You will always run into some sort of barrier. What you have to do is you have to bake the performance aspects of this into your design fairly early on. Now, this doesn't necessarily mean doing lots of quick optimizations. This is more about thinking about the way your data structures interact. They interact with the underlying important resources that your system is dealing with. And a way to tackle this is to have a set of design principles. So for Aeron, we've got a bunch of them. I'll whip through them fairly quickly. We've got garbage-free and steady state running. So this is the idea we're not allocating while we're sending messages backwards and forwards. This is both for the Java and the C driver, because you don't want to allocate the C driver on your fast path either. We apply smart batching the message path and lock-free algorithms. I'm going to go into a lot of details on these, so I'll get back to those in a bit. Non-blocking I/O. This is the idea that when we try and use an I/O system, we don't want to wait for the operating system to come back before it's ready to send the data. If we can't send data over the network, we want the operating system to come back immediately and say, no, we can't do that, and let our application deal with the implications of it. Avoiding exceptional cases is all about keeping the CPU pipelines hot and avoiding CPU stalls. Applying the single writer principle is a concurrency idea, and this is the idea that if you are writing concurrent code, try, if you can, to make sure your data structures only have a single writer. This makes the implementation of those constructs and those data structures and algorithms fundamentally simpler and a lot faster. Preferred unshared state. So this is the idea that if we want to communicate between the various threads in our system, like the sender, receiver, and the conductor, pass messages. Don't actually share data with locks and various other things. And finally, avoid unnecessary data copies. This is another one I'm going to dig into quite a bit when I start talking about the smart batching. So first off, I'll talk very briefly about garbage free. So here's a little snippet of an API. This is the offer method that we use when we're using a publication. We use our own buffer implementation. You'll notice we're not using the byte buffer that comes with Aeron.NIO, the Java.NIO. The reason for this is we think from a garbage perspective, there's a slight design flaw with byte buffer in that it encapsulates all the pointers inside the object. So if I have a larger buffer and I want to use a smaller portion of it for an IO operation, let's say like sending the data on the network or running it to a file, I might, but if I end up changing those positions and limits, I could end up changing something else that's being used elsewhere. So often people will need to make things like defensive copies. So you use slice or duplicate and these types of things. These will allocate new instances of the byte buffer. So for this reason, we actually separate out the offset and length references and do it differently, just so we can avoid these sort of unnecessary copies. I know of at least one very well-known application has a number of performance issues caused by this continuous creation of defensive copies of byte buffers in order to prevent the system from running into various errors. So lock-free. Lock-free is a really interesting idea. And this doesn't mean we don't have any locks. This means how do we deal with locks? How do we deal with critical sections? The idea that you want the system to, if one particular thread stalls for some reason, this might mean an interrupt request comes in and it gets scheduled off the CPU, or you get some sort of page fault. If you get a stall in a thread like that, it won't go and stall any other part of the system. So it's a really interesting concept. If you're using a lock and you enter your critical section and then you end up with a stall, anything else coming into that lock will have to stop and wait for it. So we want to avoid that altogether. There is interesting sorts of algorithms using compare and set, but the particular way we get around this is using an atomic increment. So I'm going to go through the algorithm that we use inside of the term buffers to implement this, because unfortunately, something we can't get around is that the term buffers end up having to be a concurrent data structure with multiple writers. If we create a publication and multiple threads are writing to that same publication, we've got to be able to deal with that. As I mentioned, these term buffers sit in memory but on a shared in-memory file system. So you can think about this as a file, but fundamentally it's a buffer in memory. And we have a single value we call the tail. And whenever we want to put a new message into the buffer, we simply do an entire increment of that tail and add the message in. Subsequently, if we get another message, we do the same thing. However, on the other side of this file, the other side of this buffer, we've got the sender that's reading. And it can't just rely on the tail value incrementing. It's got to wait a little bit longer. So it's scanning from the front to the back, processing these messages. It can see the tail move forward, but it has to wait until the header appears. And specifically, the first field in the header is the length of the message. So prior to the message being written in, the value will be 0. The sender will just sit and wait until that header length becomes non-zero. We then can continue to fill the tail up, fill the things up with buffers until we get to the very end. And at that point, what we do is we then rotate over and create a new buffer. What we don't do is have one file that continues on and on and on forever. What we actually do is we split it up into 3, and we use an algorithm that my boss, Martin Thompson, kindly calls the traveling underpants algorithm. If anybody who's ever been a backpacker before, the idea is you really only need 3 sets of underwear. The idea you've got the pair you're wearing, the pair that you're going to start washing, and the pair that's clean. And we're doing the same thing here. We've got our active buffer. We've got the dirty buffer, which is just being rotated from, which will be cleaning up in the background. And we've got a clean one that's ready to rotate into becoming the active one next. So here's where it gets interesting. What do we do when we reach the end of the buffer and 2 threads are contending on this? How do we deal with this edge case? Well, imagine we've got 2 threads. We've got message X and message Y, and they both rush in to try and write their messages. What happens is the tail increments, and then eventually it increments right off the end of the buffer. So the 2 tail values will be provided to the 2 threads. The one that's still within the buffer is perfectly fine to go and write its message in there. But the problem is, what is the one that's writing after they're going to be able to do? Well, unfortunately, it can't write its message in because there simply isn't enough space. However, it can detect that it was the message that caused the overflow. And when it causes the overflow, it knows that is the signal for it to rotate the buffer. So what it does is it writes some padding into the end of it, and then effectively triggers the rotation and writes its message into the new active buffer. There can be even more than 2 threads. There can be 3 or 4 or 5 or 6. Those messages will be incrementing the tail well beyond those, but they will be able to recognize that the tail was already higher than the end of the buffer before they did the increment. It's easy to figure out whether you were the message that caused this overflow simply by taking the tail pointer, subtracting the length of the message you were trying to write, and if you end up back inside the buffer, you will know the one that caused that. So that's how we get around the idea of this lock. This is how we implement our lock-free algorithm. But I did mention a couple of other things. I mentioned that these term buffers right at the very beginning are actually a fundamental data structure that makes a lot of Aeron work. Because as well as providing this lock-free algorithm for publication, it is also the cornerstone of providing the smart batching and data copying aspect of the principles I talked about earlier. So I've ripped a snippet of code out of the Aeron system. So this is the actual method inside of Aeron that sends data onto the network. It's called send data, funnily enough, and it receives the sender position and the term offset. Those are actually related values. The sender position is sort of an absolute value across all buffers. The term offset is the offset to that position in the same buffer. So the first thing we do is we work out how much data is available. And we actually work out what we call the available window. This is the maximum amount of data that we could possibly send. And this is the difference between where we are currently up to in the term buffers and what we call the sender limit. And the sender limit is the maximum that we could send without us being impacted by flow control or back pressure from the downstream receivers. We take that available window and we do a min with a value we call the MTU length. So the MTU, when you're dealing with networking, is the largest size of packet you can put onto the network without causing data fragmentation. What we would really like to be able to do to minimize the number of times we actually have to call send, the number of times we actually have to try and push data to our network API calls, we want to be able to pack our messages on the network with as much data as possible. So we're trying to do MTU length worth of messages all the time. This is because fundamentally, if you send 100 bytes in a single network message or a full MTU length, it's going to take roughly the same amount of time. So you want to make this optimization to get the very best out of the network. So we take what we call the scan limit. This is the minimum of the available window and the MTU length. And then we scan across the buffers in this method called scan for availability. We pass in the current term buffer, the term offset to start from, and the maximum number of bytes we want to move forward. What that then returns to us is the available. This is the amount of data that we can send. And here's where it gets kind of interesting. Each one of these term buffers, which is implemented as this unsafe buffer class inside of Aeron, has a reference to an underlying java.io byte buffer. So they're sharing the same underlying data. The reason for that is so we can interact efficiently with the Java networking libraries. So we take what we call the send buffer, and we set the limit and position on it, and then we just pass that straight to the network. So this is how we've eliminated our data copies as well. So if you imagine our publisher inside of our application, all it's doing is calling offer. This gets the data copied into these term buffers. And then we're simply passing a memory reference to the term buffers along with an offset length all the way down to the networking libraries. So we've got barely any copies going on at all. In fact, simply only one from our publication down to the network. So we can look a little bit more at a diagrammatic representation of how this smart batching works. So let's imagine a case where we've got a term buffer and a single message has arrived. While this code, the send data code, has gone off and it's writing to the network, it's picked up message 0. You'll see the available pointer is just at the end of message 0. MTU length is a lot larger, so we've taken the minimum of those. And it's sent just that message 0 onto the network. In the interim, a whole bunch more messages have arrived. So by the time we come back, we can see that the sender position has moved forward. It's now at the beginning of the first message. And then if we add the MTU length on there, we will notice that that is smaller than the available length and ends up somewhere in the middle of message 3. But I did state ahead of time that Aeron does the same thing that UDP does, in that you either get all of the message or none of the message. So what it will do is it will then go ahead and send only message 1 and 2, because that's the point where it can go without having to fragment a message onto the MTU. And then eventually it'll come back and send message 3. So that's kind of a diagrammatic representation of how the smart batching type stuff operates. So let's have a little look at archive, because I promised I'd mention that as well. Turns out that the way that we get really high throughput for archive, making that work really well, and how we get really fast disk I/O, it's the same fundamental principles. These ideas of utilizing things like smart batching and minimizing data copies. So here's a little representation of what we do inside of archive to achieve a very similar outcome. Inside of the subscription, we have a method that we call block poll. This is similar to the poll method where you receive messages, but the difference is we're not receiving individual messages, we're receiving chunks of data. So the idea is the callback to the block handler is going to give a term buffer with an offset in length. So inside of the archive method, we've got something here that we're calling image.blockPoll. Don't worry too much about the difference between an image and a subscription. A subscription is simply an aggregate of images, and when you do a block poll, you poll them over multiple ones. So we're calling this image.blockPoll. We're passing in a recording writer, and we're passing in this maximum length. This is similar in purpose to the scan length, the scan limit that we looked at earlier. A default value for this inside of archive, it's configurable, but typically we're looking at about 1 meg. So we're trying to get a good chunk of data in order to pass through down to the file system. One of the reasons we want a really big chunk of data is, unfortunately, there aren't any really good non-blocking I/O APIs for disk access in Java. Maybe we'll see some stuff come around when we get IOU ring support in Java, although I'm not holding my breath. But what is the archive actually doing? What does the actual recording writer look like? So this is our on-block callback that we're receiving in the recording writer. The recording writer is the thing that's actually writing the stuff to disk. So as you can see, we receive the term buffer and the offset and length. So this is saying, here's a chunk of data representing a whole set of messages that we're going to write to disk. And you'll notice that we actually do something fairly similar. There's a little bit of bookkeeping up front, but what we effectively are able to do is we can get the underlying Java NIO byte buffer that's represented by the same direct buffer. We set the limit based on the term offset and the data length we've received, and then we set the position as well, and then we pass that directly down to the file channel. So again, using that SPI implementation we provided, we can get this very efficient reading of this buffer that's being written to by the publication and then written down to disk with this absolute minimum of data copies. Now there is one fundamental idea that makes this all work. And this is one of the early design ideas, and it's the sort of thing you can't get wrong up front. If you don't design with this, you don't get the benefits. And this idea is that the layout in the data of the term buffers that come from the publication, come via the publication, the layout of data that's on disk for our archive, and the layout of data as it transits the network in those network packets is exactly the same. It has the same data layout. Had we not designed this in early, there would be the benefits we could get of this very low number of data copies. Because if there was any subtle changes in the data layout, it means that we'd have to do a transformation. It means we'd have to take the data from the term buffers, copy it, modify it before writing. And that's effectively double the amount of data copies we're trying to get on this really fast path. So it's little subtle things like that can make a big difference to building a very high performance system. So that kind of brings me to the end. Those were all the main ideas I wanted to convey today. I'm really hoping that everybody got a little bit of something out of this talk. What I hope is, one, just expose you a little bit to Aeron, expose you to the sorts of performance you can get while using it. It might be a really great solution in some of the systems you're working on. But also, if you are challenged with building some interesting high-performance systems yourself, perhaps some of the ideas, either in terms of the specifics around batching and minimizing data copies, or from a high level about thinking about things from a principle-based approach. Perhaps you're working on some stuff like big data analytics or building games on top of GPUs, thinking about the important aspects of those, how the hardware works, and trying to morph those ideas into a set of design principles that you can apply as you're building the system and think about it that way. So that brings me to the end. Thank you very much for listening to me today. Here's a couple of references if you're interested in learning a little bit more about Aeron. You get links to our wiki. We've got the design principles and a little bit about Aeron archive as well. Thank you very much.
Thanks, Micah.
And we got